great exercise and fun, there's nothing like spending an afternoon at a swimming pool. A public pool can hold large numbers of people. Without proper maintenance, it could also be home to large numbers of bacteria. How do swimming pool technicians ensure that the water is safe for swimmers? It's all connected to chemistry. In this program, we'll learn about the chemistry of swimming pools using Bronsted-Lowry theory and neutralization equations. We'll calculate the amount of chemical needed to maintain a safe pH in swimming pools. We'll do acid-based titrations and see how a pH probe attached to a computer is used to produce a graph called the titration curve. We'll use various combinations of acids and bases to generate titration curves. We will analyze the strong acid, strong base titration curve and do calculations to predict the pH at various points on the curve. And we'll learn about the applications of neutralization reactions and the information we can gather from titration curves.
Swimming pools contain hypochlorous acid as a disinfectant. Hypochlorous acid can easily penetrate the cell wall of a bacterium. Once inside the bacterium, chlorine and oxygen in the acid oxidize the protein of bacterium, destroying the organism. A pH of 7.5 ensures that the appropriate amount of hypochlorous acid is present to keep the bacterial count low. If the pH of the pool is too high or too low, how can it be adjusted so that it's just right? At many large community swimming pools, hypochlorous acid is produced by bubbling chlorine gas through water. Other safer sources, such as solid sodium hypochlorite or calcium hypochlorite, are used for backyard pools or hot tubs. They react with water to produce hypochlorous acid. An equilibrium exists between the hypochlorite ion and hypochlorous acid. If the pH is too high, muriatic acid, also known as hydrochloric acid, is added to community swimming pools. An acid like sodium hydrogen sulfate is added to hot tubs or backyard swimming pools. When the pH is too low, a base, such as sodium carbonate or sodium hydrogen carbonate, is added. Decision on which chemicals to add is based on pH, cost, and safety. Let's now connect the chemistry of a swimming pool to a Bronsted-Lowry neutralization reaction.
Here at the swimming pool, ideally we would keep a pH at about 7.5. If it was higher, we would lower it with an acid, and we would raise it with a base. And this is a kind of problem that we might encounter. What quantity of sodium carbonate would have to be added to a swimming pool containing 1.7 times 10 to the power 6 liters of water to raise the pH from 6.8 to 7.5?
Helen has been working on this problem, and the first thing she's done is written a Bronsted-Lowry neutralization reaction. All right, let's have a look. Helen, you've got two reaction steps. Why?
That's because sodium carbonate is a base that accepts two protons in this reaction.
All right, so this is your first reaction step. The first proton is accepted. Second reaction step, second proton accepted. And your net reaction. So you'll use the net reaction in the calculations. Let's have a look at the first part of the calculation.
Okay, so the hydronium ion concentration of pool water at the pH of 6.80 is 1.6 times 10 to the negative 7 moles per liter. And the moles of hydronium ion in 1.70 times 10 to the 6 liters of pool water at a pH of 6.80 is equal to the concentration times the volume, and that gives me 2.7 times 10 to the negative 1 moles.
Good. And Helen has written the rounded value here just for convenience, but she is holding all the unrounded values in her calculator until the final answer. Right, Helen?
That's right.
All right.
Okay. Now the hydronium ion concentration of the pool water at a pH of 7.50 is 3.2 times 10 to the negative 8 moles per liter. And the moles of the hydronium ion in 1.70 times 10 to the 6 liters of pool water at the pH of 7.50 is equal to that concentration times the volume, and that gives me 5.4 times 10 to the negative 2 moles.
All right, Helen, so now you have the moles of hydronium at both pH levels. What do you do next?
Okay, I figure out the required decrease in the mole of hydronium ion, and what I do is I take the moles at pH of 6.80 minus the moles of the pH at 7.50, that gives me 2.2 times 10 to the negative 1 moles. And so I calculate the moles of carbonate ion required, and I do that by taking the mole ratio,
That's from your Bronsted-Lowry neutralization reaction.
yeah, times 2.2 times 10 to the negative 1 moles, and that gives me 1.1 times 10 to the negative 1 moles.
Good. All right, let's go on to the last step.
So now the mass of sodium carbonate required is equal to 1.1 times 10 to the negative 1 moles times 105.99 grams per moles, and that gives me 1.1 times 10 to the 1 grams, which rounds off to 11 grams.
Good. All right. So that means that 11 grams of sodium carbonate is required to change the pH of this pool from 6.80 to a comfortable 7.50.
You'll find it in almost every kitchen, a most versatile substance, such an unassuming package. It's remarkable. And I'm referring, of course, to sodium hydrogen carbonate, or baking soda. Now, baking soda enables us to bake fluffy muffins and cakes, but how does it work? Well, the hydrogen carbonate ion neutralizes the lactic acid in milk to produce carbonic acid, which breaks down into water and carbon dioxide gas. Now, the carbon dioxide gas is trapped in the dough and forms little bubbles, which produce light cakes. Used as a toothpaste, it neutralizes the acid in your mouth to help keep your teeth clean and white. Want to help the environment and save money? Well, baking soda is a great cleaner for your home. Use it as a mild abrasive, as a carpet deodorizer, or as a mild basic solution to clean grease in the kitchen. Why is a solution of baking soda useful in chemistry laboratory? Well, hydrogen carbonate ion is amphiprotic and can neutralize both acids and bases. And it's so gentle on skin, you can use it in your bath. And why is baking soda environmentally sensible? We'll provide the answer at the end of the program. Sodium hydrogen carbonate, a very useful substance.
Titration is a valuable tool used in quantitative analysis, used so that we can determine the unknown concentration of a solution. And Robin has the titration apparatus set up. Looks like you're adding sodium hydroxide to hydrochloric acid. And what we're going to do is see how a titration curve changes as this progressive addition occurs. Now, the reaction equation that we'll be dealing with can be seen here. First of all, we have the double replacement version, hydrochloric acid plus sodium hydroxide, producing liquid water and sodium chloride. At the bottom, we have the Bronsted-Lowry version of the same neutralization reaction. So, Robin, can you tell me a little bit more about your design here?
Okay. In the beaker, I have a 0.10 mole per liter hydrochloric acid solution, and I'm going to titrate that with 0.10 mole per liter sodium hydroxide. And so in the beaker, I've also got the magnetic stir to keep things stuck,
Right.
and the pH probe, which is connected to this interface, which is going to send the data over to the laptop where we're going to get a titration curve.
All right. Well, looks like we're all ready. We might as well get started.
Okay. I'll open the burette.
Just get a steady series of... Okay, good.
Okay. pH looks like it's rising, but it's not rising very quickly.
No, it's a fairly gradual rise. First.
But as it goes on, it seems to get a more sharp, drastic rise.
Yeah, it's going right up past the pH of 7 and way up into the basic range.
Now around 12 again, it seems to sort of taper off, and it's still rising, but not as quickly.
All right. So we have our initial fairly, well, it's not flat, but a gradual rise followed by a steep increase followed by another fairly gradual rise.
Should I?
Yeah, we'll stop then. And what we'll do then is have a look at this titration curve in a little more detail in just a moment. You're looking at the titration curve that Robin just generated a moment ago. What we're going to do is use mathematics to analyze 3 different sections of this curve, starting with the point, Robin, before we added any base whatsoever.
Okay, starting at that point, in the beaker we have the initial amount of hydronium ion, which is 2.0 times 10 to the negative 3 moles. We have no hydroxide ion since we haven't added any sodium hydroxide. So the reagent in excess would be the hydronium ion, 2.0 times 10 to the negative 3 moles of hydrochloric acid. To find the equilibrium concentration, we divide out the reagent in excess by the total volume of the solution, which at this point is still 20.0 milliliters. And then we get our equilibrium concentration to be 1.0 times 10 to the negative 1 moles per liter. And the pH of that then would be 1.00.
Okay, now this corresponds to the section of the titration curve, which is right down here at the beginning. All right, now suppose we add almost the same volume of base as we had acid, 19 decimal 0 milliliters compared to 20 decimal 0. What does that give us, Robin?
Well, we have 19 milliliters of sodium hydroxide, 20 milliliters of hydrochloric acid, but that still means that we do have a reagent of excess, the hydrochloric acid, 1.0 times 10 to the negative 4 moles of excess hydrochloric acid. Now we divide that by our total volume to get our equilibrium concentration, 2.6 times 10 to the negative 3 moles per liter of hydronium ion. The pH then is 2.59.
All right, so even though we have almost the same volume of base as we had acid, the pH doesn't go up terribly dramatically. It goes from 1 to 2.59. All right, now what?
The next entry we have in our chart is where we have added 20 milliliters of sodium hydroxide to the 20 milliliters of hydrochloric acid. And so that means we have no excess, since we have equal amounts of the solutions, and the solutions are in equal concentrations. So our equilibrium concentration will be 1.0 times 10 to the negative 7 moles per liter, and the pH would be 7, which is neutral.
Right. Now, it's really dramatic when you think of it this way. Previous to this, we had 19 milliliters of added base to our acid. Now we've added 1 single milliliter extra to bring us to a total of 20 milliliters of added base. The change in pH from 2.59 all the way up to 7. Okay, now what?
Well, since the solution we have is already neutral, if we were to add any more base, it would become much more of a basic solution. So here, when we have 25 milliliters of sodium hydroxide added to the 20 milliliters of hydrochloric acid, our reagent in excess is going to be the sodium hydroxide, and that's going to be 5.0 times 10 to the negative 4 moles of excess sodium hydroxide. To find our equilibrium concentration, we divide that reagent in excess by the total amount of volume, or the total volume, of the solution, and we get 1.1 times 10 to the negative 2 moles per liter of excess, or equilibrium concentration. And the pH we get from that is 12.05.
All right. Of course, that corresponds to the high part of our titration curve, the part where the base is in clear excess to the acid. Well done, Robin. We're going to analyze that titration curve in even more detail in just a moment. But first, we're going to consider something that is really moldy.
Did you know that extract from this green material on the orange has the potential to cure many illnesses? The discovery of the drug penicillin was one of the most important medical achievements of the 20th century. This is an example of an accidental discovery. Dr. Fleming was studying bacteria and did not want mold growing on his culture plates. He noticed that where mold was present on the plates, bacteria did not grow, and he wondered if it would have the same effect on bacterial infections in the human body. Fleming's discovery marked the beginning of an age of miracle drugs called antibiotics. Some drugs, such as penicillin G, are weak acids. They have low solubility in water because they are nonpolar molecules and can't be absorbed into the bloodstream from the intestines. To solve this problem, the sodium salt of penicillin G, which is polar, is used instead and is just as effective.
We're back with the titration curve showing the hydrochloric acid, which initially had a pH of 1, to which we added our sodium hydroxide solution of the same concentration as the acid. But as we did this initially, the pH didn't change much. It was relatively constant. Why was that, Robin?
Well, that's because even though we were adding sodium hydroxide to the hydrochloric acid, the solution still had an excess of acid, so the pH was relatively low.
Good. But eventually we'd reach the point where we'd have almost equimolar amounts of acid and base, and then equivalence. Now, how do we define the equivalence point, Robin?
The equivalence point is a point in a titration where moles of acid and moles of base are equal.
Okay, and where would we find it on our curve?
That would be this point right here. Now, if we were to draw a vertical line downwards to the x-axis, we would be able to find out at what volume of sodium hydroxide we'd reach the equivalence point.
Great. Now, is there any other information the equivalence point can give us?
Well, if we draw a horizontal line from the equivalence point to the y-axis, we would be able to find out at what pH we reach the equivalence point.
Okay, now beyond equivalence, what we have is an excess of base, and that's why the pH is high in the basic range. And if we continue to add our base, we reach another level where the pH doesn't change very drastically. It's almost constant. Next, coming up, what does neutralization have to do with acid rain?
Alkalinity in fresh waters is determined by the dissolution of carbon dioxide and the subsequent equilibrium that results. Carbon dioxide, when dissolved in water, will combine with water to form carbonic acid, which in turn will dissociate to form hydrogen ion plus a bicarbonate ion. The bicarbonate ion will dissociate into the hydrogen ion plus a carbonate ion, and then finally both the bicarbonate and carbonate will dissociate to produce hydroxyl ions. We also have to be aware that in most natural waters in Alberta, there are a variety of other anions that can contribute to buffering. And if we were to make a true representation of alkalinity, we would be measuring the buffering capacity due to bicarbonate, carbonate, the hydroxyl anion, plus organic anions, and correct for the hydrogen ion typical of the pH where the water sample is measured. So in nature it can be quite complicated, and because Alberta has a wide range of geological conditions, we have a wide range of water types, and so there's a variety of materials that can contribute to buffering or to alkalinity. Typically what is done is a crew will go out into the field, take samples from a lake or from a river, and they're stored in polyethylene containers. And the container is put into a cooler and transported in dark, cool conditions back to the laboratory where the titration begins. The basic concept is you add acid, you record the pH, which begins to decline, and then we do a titration curve which relates how the pH drops as acid is added. And this is the curve here. Say we're starting here at 9.5. We start adding acid. The first component goes as hydroxyl ion, and then we go down to the next inflection point. We've used up the carbonate anion, and so on. Then we use the bicarbonate anion. And these changes in pH are recorded with each increment of acid, and the curve is so produced. And then applying it to the Alberta scene, we want to understand how well buffered our lakes are, how much alkalinity our lakes have, because the more alkalinity a lake has, the less likely it is to be affected by acid rain.
You've already seen how titration curves can help monitor changes in the environment. Well, Helen and I are going to look at a different type of titration curve, a weak-base strong acid titration curve. So Helen, why don't you tell folks at home exactly what's in our apparatus here?
Okay, we have a titration apparatus here. We have 0.1 mole per liter of hydrochloric acid in here and 0.1 mole per liter of ammonia in here.
Right.
And in here we have the pH probe, and that's connected to the computer. And the computer will generate the titration curve as we titrate.
Precisely. So I'm ready to start. Why don't you go?
Okay.
You can see the little magnetic stir is just whirring away quietly there in the corner. Okay.
Okay.
Well, it started already. What do you notice?
Okay, it's at a high pH, and then it's slowly dropping.
Now
and there's a big vertical drop towards the equivalence point.
And past it even, right?
Yeah.
Now it's starting to level off the bottom.
And
Why is
that's
that happening?
when there's an excess of acid.
Excessive acid. Okay, we'll let it run for one more second. That should be good. Now I'm going to reformat this and put it up on the big screen so that Helen can help us analyze it. Aha, there it is.
Okay.
So point out the parts that we were looking at before.
All right, the initial pH started at approximately 11, then it gradually drops here and reaches the equivalence point at about pH of 5.
Right.
And then as more acid is being added, it levels off right there because there's an excess of acid.
Perfect. That's nice. Okay. You know, we can really learn a lot about this, though, if we superimpose a strong base, strong acid titration curve right on top of it. There it is. What are the differences that you notice, Helen?
Sodium hydroxide being a strong base, it's at a higher pH, and so that makes the vertical drop even longer, and
Right.
that makes the equivalence point higher at pH of 7 as opposed to pH of 5 of the ammonia, and then they level off at the same pH.
Does it make sense that they level at the same pH?
Yes, because of the hydrochloric acid.
Right, it must be the same concentration too. Good.
Yeah.
Is there anything that's different about the first part there of the two curves?
I was just wondering about this ammonia curve, why
It drops faster, doesn't it, than the NaOH curve? Why is that? Well, the answer is really quite interesting. And here's what it has to do with. When sodium hydroxide reacts with hydrochloric acid, what's the product?
Water.
Water, right, with a neutral pH. But when ammonia reacts with hydrochloric acid, one of the products is the ammonium ion, NH4 positive aqueous, and it acts as a weak acid. And so that tends to drop the pH at a faster rate in the beginning there than in the strong base, strong acid titration. Does that make sense?
Yeah.
Okay. So keep that in mind when you're looking at titration curves, the difference between strong base and weak base with strong acid titration curves. And now, food additives and what they have to do with neutralization. Helen, I really liked how you did that point. That was fabulous. Did you know that many food additives are either weak acids or salts formed in these acids by neutralization? Example, salt and vinegar potato chips, which happen to be my favorite. Do you know what gives them the vinegar flavor? Well, it's the sodium acetate. When it reacts with water or saliva, it forms acetic acid, or vinegar. Salts are sometimes added to improve the nutritional value of processed foods. These include ascorbates, salts of vitamin C, beta-carotene, vitamin A, ferrous sulfate, source of iron, riboflavin, vitamin B, zinc sulfate, mineral supplement, and many others.
Helen has begun titration of acetic acid with sodium hydroxide. The computer interface is now generating a titration curve. Let's have a look, Helen.
Why doesn't the pH start at 1?
Well, the pH does not start at 1 because acetic acid is a weak acid and it does not ionize completely. Now, we should be able to calculate the very first point on this titration curve. All right, let's do that.
Well, using this equation, I can use that to write the equilibrium law expression.
Good.
And since the acetate ion and hydronium ion are formed at the same time, their concentration is the same. And so then I can substitute in the numbers and determine the hydronium ion concentration and use that to determine the pH.
Good. So you've calculated the pH to be 2.87. Let's have a look in the curve. Does it start at 2.87?
Yeah, it does. And then it slowly rises to the equivalence point, and then it rises rapidly and levels off when the base is in excess.
Good. Now, let's take the titration curve that was just generated and redraw it. Here we have our weak acid with the strong base represented by the yellow line. Now let's compare that to the titration curve of a strong acid with a strong base represented by the green line. If we examine the rise, we can see it's much larger in a strong acid compared to that of a weak acid. We also can compare the equivalence point. In a strong acid, the equivalence point is around 7. In a weak acid, the equivalence point is above 8. We can also compare the beginning of the titration. In a weak acid, the one that we've just done, the beginning of the titration was a pH of 2.87. Let's compare that to a strong acid, and it should begin around 1.0. Now that we've looked at these two titration curves, let's examine another one. That is the one with a strong acid and a base that can accept more than one proton.
We've already seen a number of titration curves involving monoprotic acids and monobasic bases, but now what we're doing is generating a different titration curve for the titration of sodium carbonate with hydrochloric acid. So Robin, how's it looking here?
Well, it looks like one equivalence point has already shown up. But now as I watch, it looks like another one is developing.
Aha, 2 equivalence points. Well, we're going to have a closer look at that. We have a computer printout of the titration curve for the titration of sodium carbonate with hydrochloric acid. And on the paper here, we have 3 reaction equations. So, Robin, what do these equations have to do with the titration curve?
Okay. At this part of the titration curve, we can see that there's an excess of the carbonate ion. This continues to approximately here, where we can estimate the first equivalence point to occur. Now that corresponds with the first equation we have written down. The hydronium ion plus the carbonate ion gives us the hydrogen carbonate ion plus water. If we continue down the titration curve, this part of the curve shows us an excess of the hydrogen carbonate ion. And this again continues to approximately there, where we can estimate the second equivalence point to occur. And we see the second equation with the hydronium ion plus the hydrogen carbonate ion giving us carbonic acid and water. Now those 2 equations we can combine to a net reaction of 2 hydronium ion plus the carbonate ion, giving us the carbonic acid plus 2 water.
Okay, great, Robin. Thanks. So there you have it. 2 reaction equations, each one corresponding to one of the equivalence points on our titration curve. And overall, the entire titration curve is represented by the net reaction equation that we have.
Helen has just performed titration involving an unknown acid and base of equal concentrations. Now, we've generated a titration curve, and Helen is going to tell us whatever information she can from the curve. All right, Helen?
Okay, the initial pH is about 2, which tells us that it's a weak acid and not a strong acid, because then it would have started at a pH of about 1.
Correct.
The first vertical rise is where the first proton is being neutralized. And if we draw a vertical line from the equivalence point from there, that tells us the volume of base needed to reach that point. And a horizontal line from that equivalence point will tell us the pH of the equivalence point.
All right, now what about this section of the graph?
The second vertical rise is where the second proton is being neutralized. And a vertical line drawn from that equivalence point will tell us the volume of base needed to reach that point. And a horizontal line drawn from that point will tell us the pH of that point.
Correct. How about this region right here?
That's when the base is in excess.
Good. So now, I can tell you that the unknown acid is phosphoric acid, and the unknown base was sodium hydroxide.
Okay. If it was phosphoric acid with 3 protons, why is there only 2 equivalence points on the graph?
Well, good question. Now, the third acid with the third proton to be donated, hydrogen phosphate ion, is a weak acid, and the third step there is not quantitative.
Okay.
All right, so now let's review titration curves and see what they can tell us. First of all, you can see that how the strength of an acid or base involved in a neutralization affects the shape and appearance of the titration curve. You can immediately see whether the neutralization involves a polyprotic acid or basic species from the number of equivalence points indicated by the vertical portions of the curve. And you can tell from the point where the titration starts whether the solution being titrated is an acid or a base, and if it's strong or weak. So, titration curves tell us a great deal about neutralization reactions.
In this program, we examined neutralization reactions, and we did a stoichiometric calculation involving neutralization. We drew titration curves and plotted volume of titrant against pH, and we used the computer interface to generate 5 different titration curves. We saw that neutralization reactions are important in our everyday lives and important in industry. We also saw that acids and their conjugate bases are used to preserve foods and increase the nutritional value of our food supply. And we saw several useful neutralization reactions involving sodium hydrogen carbonate. Now, before we go, one last thing. The answer to why sodium hydrogen carbonate is environmentally friendly. Well, first of all, it's water soluble. When sodium hydrogen carbonate reacts with water, it forms carbonic acid. Now, the carbonic acid decomposes into water and carbon dioxide gas. If the sodium hydrogen carbonate reacts with a base, the products are water and the carbonate ion. All of these products are commonly found in the world around us.
Okay, so
All right, Helen, so now you have the moles of hydronium ion at both pH values. Now what do you do?
okay, I figured out the required decrease in moles of hydronium ion. And I do that by taking the moles at the pH of 6.80